So, living in the matrix. My introduction or my justification on this is that about once a year, I go into statistical research, math research, and I fall back on or utilize commercial matrix-oriented software, such things as Octave and MATLAB. And my head scratcher problem is that the syntax is so complicated. I dig out the book and I start working my way through all the parentheses, brackets, and braces, and struggle with trying to figure out. So what I'm looking at now is how to do it in Forth. So today what we're going to cover is a little bit of the traditional matrix syntax that you'd normally see in textbooks, a Forth appropriate syntax, and then finally a Forth matrix extension word set that follows that syntax, and then some operations on matrices and the matrix calculations. The credits first. My work currently is done on Win32 Forth, which was developed initially by Andrew McEwen in about 1993-4-5. Passed it on to Tom Zimmer, who really expanded it and polished it up. Bob Smith did the floating point, and then the European team has updated it from about 2004 to about 2012. And finally, a key concept in all this was the matrix structure and parameter used by Dr. Julian Noble. He wrote the book Scientific Forth in 1992. It used a Forth called HS Forth, Harvard Software Forth. Was very advanced for its time. Memory management was a problem. It observed and utilized to great advantage the memory management that the operating system had at that time. Remember, this is pre-Windows. This was DOS segmenting. Good news, bad news, it was very productive for its time, but the problem now is that weaved throughout all of his code is a lot of segment memory management, and that's confusing to say the least. But anyway, that book is a goldmine, a resource, and in it he used this matrix notation, which I believe he credited to someone else briefly, but I can't remember that. The book has very limited availability. There's a GitHub site that is trying to reset it and republish it, and they received permission from Julian Noble's wife to release the copyright. He passed away about 6 or 8 years ago. So we'll go through the operations as a user would see, sort of top down. The first step you'd want to do is to create a floating matrix. And so you specify the row and columns 3 and 4, then a create bracket F first. Now the convention here is that every matrix has the left brace in its title. This tells you that on execution, it will give the address of the matrix. So the F indicates this is floating point. Instead, if you go 3, 4, 8, you can create the same thing, but if you want a cell matrix, you go 3, 4, or if you want a byte matrix, you go 3, 4, 1, create. If you want a word matrix, you go 3, 4, 2. If you want a cell, you go 3, 4, 4. And if you want floating, you go 3, 4, 8. In other words, you can specify the storage site. And so if we create the matrix shown by first brace at the top in green, and then follow that by the right brace list, see the contents, and it's initialized to 0. To do some direct data entry. Direct data entry, we would specify again our matrix, which is first, and then we have that little green left brace, left bracket. That indicates the start of a literal string. The first brace, the matrix name knows its dimensions, rows, and columns. so that what follows has to be the specific number of rows and columns, and there's error checking if they don't match. So the 1, 1, 1, 1 is the first row, 2, 2, 2, 2 is the second row, and 3, 3, 3 is the third row. And then with the second line, we see the green list. That shows us indeed the matrix has been initialized with floating point values, first row, second row, third row. To simplify setting up and testing, we can fill a matrix full of integers. So in this case, the operator that's the second row green is the right brace list. Fills the right brace fill fills the matrix with its values 0 through 11. This is a quick setup for testing. Now finally, we do some matrix math. In this case, if we the syntax is that we have the source matrix, the matrix operated on, and then the matrix that is the conclusion. In this case, we're going to take data from the first matrix, add it to itself, and return it to itself. In this case, we could have up to 3 matrices: the source, the operator, operatee, and the destination. So again, we'll take that matrix we just created a moment ago that goes 0 through 11, we'll add it to itself, and sure enough, here is 0 through 22. Now we get into some of the more interesting things, which is transposing a matrix. In this case, the matrix is exchanged rows and columns. So in this case, we fill a matrix full of integers 0 through 11. Then we, on the second section, we do the transpose that's in green, and we do the list. And notice that that matrix now has had its rows and column dimensions interchanged, and the contents have been shifted row-wise to column-wise. Just what you'd expect. Now, here's where it gets interesting from a comparative technology standpoint. In the traditional matrix syntax you can see taken directly from MATLAB. We see the C is a variable name. Then in the square brackets are cells within the matrix. And it's in the first one, it's 1 semicolon 3, which means row 1, column 3. The math is done as you would expect. A and B are added together and they are returned to C. So very typical, just what you'd expect. Here's the equivalent that's done in my matrix fourth. The the term of accessing A at row 2, column 2 is shown as A left brace. The double braces, which say we are now going into the matrix, 2 and 2 are the cells we're addressing. And then the right double brace says return its address. And then finally, fetch gets the value. So to review that, we specify a matrix. With the double braces, we say we are going inside the matrix. The 2, 2 says where we're going into. Then the double right braces returns the address, the actual floating point storage address within the matrix, and then we add together. So we see that the syntax is really simple, and this is the case of, you might equate it to accessing a variable. You'd say, give me the variable name, fetch from it, give the variable name, store into it, give me the variable, and store into it. Notice we're more verbose than the traditional semantics, because in the traditional semantics, as I will see in a moment, a large number of options exist. There's many combinations of combining the terms within the matrix notation. And in our fourth notation, it's more verbose because we're showing each step individually without any confusion. So the good and the bad. The traditional syntax, it's certainly very terse, very brief. You can accomplish a huge amount of activities in a small number of character strokes. But look at that third red line. This is sort of hypothetical, but this is what you get up against. On the left-hand side, you've got in the C brackets, you've got a range of columns. In the middle one, you've actually got a mention of a matrix within a cell, and on the B side, you've got selected row and columns. You're taking with the B1, 2, you're taking rows from 1 to 2, and in the left side, you're taking rows 3 to 4. This is where I hit the wall, because every time I would start a new project, I'd have to dig the book out, remember the syntax, and they do not give an overall syntax of the process. The book will tell you one element at a time, but does not clearly show the interaction between the elements. So that was my frustration. So to go to it in detail, here is the analysis of one expression. In fourth, the A bracket, the A left brace gets the address of the matrix. The double brace gets a descriptor, and that descriptor has rows, columns, and size. Puts that on the stack. The 2, 3 specifies the row and column, and then the right double brace, that one does the work because it's taking 6 parameters, and from those 6 parameters, it's locating the storage address. And if you say that's where the magic occurs, it also, the nice part is that's where the complexity is concealed, because at that double right brace time, you're manipulating 6 parameters without having to handle them or touch them individually. Just a quick review then, you can see the second green row is the operations that are visible to the programmer. At the bottom are the stack values. So the A left brace gives us an address, the RC gives us the column coordinates, the double brace gives us the address, and then the on the floating point stack, we get the actual contents. So here's a programming example. Here's the actual code for the fill command. The dupe setup loop sets up the row and column. The row number goes into the first do. So we're doing this over rows. The C is duplicated. It goes into the second do, which says over the columns. And now we're using the low-level operators. So we can duplicate the matrix address, do some row and column I and J operations to it. And since that is an integer value, it has to be converted to floating point with the S to V to F. Finally, then here's now our fourth syntax where we do the over IJ double braces F store, and that does the work of the actual storing. We loop over columns, loop over rows, and we have a couple input parameters which are dropped. So what is essentially 2 lines of code, we have developed the method to fill a matrix. This is the D chart of it. D chart is shows how we set up the loop over the rows, over the columns. We get the cell number, we store it, next column, next row. We carry the column value through this whole calculation. We drop it, and we drop the matrix address, and on the and there's no values left on the floating point stack. So here's some details on this. The first one that Julian Noble said this is in contrast to normal matrix work, which normally the matrices coordinates start at 1. In this case, they start at 0. Well, as I began doing this, I was frustrated, and I said, I want to do both. And so I put in an offset value so that you could selectively work on a 0-based system or a 1-based system. I quickly found out that that was impractical. The level of internal complexity skyrocketed. And so I have gone back to Julian Noble's suggestion, which is all the matrices are 0-based. So when you create a matrix with dimensions 2 and 3, it means that at the row value of 2, the valid rows are 0 and 1. You have 2 rows and they run 0 to 1. If the column value is say 7, then the valid column values are 0 through 6. As a set of conventions, words with a left brace or right brace operate matrix to matrix. The double brace signifies we are going into the matrix and we're operating cell by cell. So here's a word summary. Typical words would be creation words, are to create a general matrix, row, column, and size, or a floating point. The support column, these are words that were developed very, very early on because they allow us to fill, list, test, see what we're doing. The data entry words is extremely useful to be able to quickly set up a matrix and put in test values. The matrix manipulation values are what you'd expect: transpose, invert, determinant, I, and so on. Matrix math, this again works matrix to matrix. So if you're adding two matrices together, you have the right brace plus. The fancy one, the complicated one, is the dot matrix, the dot multiply, dot product. So the very one there on the matrix math right is the right brace dot star, which is matrix multiplication. Other ones are such things as row and column interchange, stack access words that in this case you have matrix addresses on the stack and you are manipulating them. In other words, you are moving the matrix address around on the fourth stack. And finally, then the cell math, which is down at the bottom, such as we'd expect, fetch, store, and plus store. Now, this is almost a conclusion, and this is where we are and where we're going. This operates at 4 levels. The first level is what I call level 0, which is the internals. These are the words that you would see when you're doing internal programming, such as the RC conformal, lets you know you have two matrices that are row and column conformal. Double brace bytes tells you the number of bytes that the matrix occupies, the storage space, and so on. Level 1 is what we do cell to cell. So it's the double brace on both sides, fetch, store, and so on. You can address cells, you can manipulate cells. Level 2 is where the current work is going on, and this is where we operate between rows and columns. This is the complexity of the original syntax, because compressed within that syntax are the ways to pick the statements apart and figure out which are rows, which are columns, and how they're manipulated. So this is what I'm currently working on. And finally, level 3 is the matrix level. This is what you see visibly: creating matrices, the fill, the list, the copy, and so on. So to wind up, I use MATLAB and a clone of Octave. I love MATLAB. It's fairly well documented in books. Octave is apparently a public domain, academic clone, and anytime something is done to MATLAB, the people who maintain Octave clone it and put it into Octave. So I think in Octave, I've only found like 2 or 3 deviations from MATLAB over the entire scope of the language. And it is very good, very popular. So as I said, I have this project once a year. The learning curve is too steep, or the relearning curve. Manuals help, but they are not definitive. And therefore, the key part is I want a reverse Polish syntax that needs no refresher course. The idea is you will know exactly what's happening because you see the order of the fourth words, and that will explain exactly what's going on step by step. And the answer is matrix fourth. So here are my references. Go to GitHub with my name, Bill Ragsdale, and the source code for the current version is posted under matrix fourth word set. And for you users of Win 432, I will offer you a treasure trove gold mine. I've been using Win 432 for 8 or 10 years, something like that. And again, every time I come back to it, I learn something new. And I got tired of having to try to remember it and relearn it. So I wrote a book. So there's a 65-page book online that is a user's guide to Win32 This is a work under development. It's a Word document. Again, 60-some pages. There are chunks mentioned into it which are gaps and question marks because this is essentially my personal notebook. But it does an exhaustive explanation on the ins and outs of Win32 And that concludes my formal remarks. Do I have any questions? I see
I have a question, Bill.
I see we're in stunned silence, and that's okay. What's the question, please?
Yeah, what about where you have a matrices of equations rather than of actual values? Have you been thinking about that?
Okay. Normally there are 3 elements in sequence. The first is the element that we're sourcing from. The second element is the one we're operating on, and the third element is the destination. So if we are adding 3 matrices, we would declare matrix A, then matrix B, matrix C, and then matrix addition. So that is the from, the operate on, and the destination. Now, if you want a matrix to add to itself, you would state it 3 times. So you'd say first, add together, and it'll essentially double that matrix. It'll add itself to itself. On the other hand, if you wanted to multiply 2 matrices back to the first, you'd go matrix, first matrix, second matrix, first matrix. So the first and second will be multiplied together and end up in the third.
Yeah, what I'm talking about is where the matrix is actually the equations, not the values. In other words, when you solve the matrix, it would go out and solve the equations that are in the matrix to produce the answer. Because, say for instance, all the values in the matrix may have some correlation with each other that's defined by the equations. And you don't know what it is from the beginning. It's not like they're real values yet. They haven't become values, right? It isn't until you apply the matrix to a particular condition that the values take on meaning. Does that make any sense?
No, it makes sense to Dave Jaffe because he's nodding, and it doesn't make sense to me. If you're solving a linear equation, then you need a set of operators to solve a linear equation. You're saying there is information encoded within the matrix, and you're trying to determine that information. And that,
no, I think what he's trying to say is that the row column are not values, but could be variables or a combination of variables and constants. And these variables depend on other things like temperature or whatever. Is that right?
Or
Dave,
and Bill, another possibility is that it's an execution token as the contents of the cells, and so they have to be executed in order to produce a value.
Yeah, but it sounds like you're talking about what I'm maybe using the wrong term, but it's symbolic execution that in matrix coordinates, you are putting in essentially code for the operation within that element. Well, that may be level 5 or maybe level 6 or 7 when we get to it someday. Right.
Okay.
Right now, I am working on inverting matrices, and I am doing like echelons of matrices, and so it's all row and column expansion. And maybe 4th day in 2021, we'll get to this.
Okay, but that's it. You got it, Bill. That's what I have in mind. Yeah. Because that's otherwise it's you have to I would like the connections attached as a matrix rather than the connections attached as external equations.
Well, in MATLAB, they have, I forget what the terminology is, but they have a way to, inside each memory cell is a matrix. So you now have a matrix of matrices, so that every time you you take a cell XY coordinate, inside that is a matrix. And now they're operating 2 levels down. And that's again where picking apart what actually happens, you can take 20 minutes on trying to analyze one set of parentheses and brackets, trying to pick apart what happened. Anyway, that wraps up. Any further questions or comments, and we'll pass back to.
So my understanding is Dwight has volunteered to implement that, and I'm looking forward to hearing his talk. So Don is with us. I'd like to say that Mitch, before the meeting, actually sent me an email begging off. He's some other personal commitments that he needed to focus on, so he won't be joining us today at all. I see Don is on the list. He says he's ready to go. So introduce yourself